Let me see. So let me just make sure I'm on my. Okay, sorry. Just want to make sure you can hear me. Let me share my screen. Okay, so then we've got lesson 16, section 16, inverse functions. So functions are super important, especially when we move forward into exponents and logs, because exponents and logs, surprise, are inverse functions of each other. So, in order to help us understand exponents and logs better, we're going to learn about just inverse functions in general. If you're moving on to pre-cal or any kind of trig, inverse functions are big there too. So, what do we have? Determine whether a function is one to one. That just is like fancy for like AKA invertible. AKA invertible. And then determine if two functions are inverses or not. Find the inverse function and determine its domain of range. Graph an inverse function given the graph of the original function. Okay, so one-to-one function. A, a function f is one-to-one if when f of a is equal to f of b, then a equals b. For any a and b in the domain of f, aka each output value y corresponds to exactly one output value x. Okay, this is a very long-winded way to say the horizontal line test. Okay, so basically that is just restating the horizontal line test. Or I'll move it up. You know, that little box is there. The horizontal line test intersects the graph more than once when the graph does not represent a one-to-one function. Okay, so I know that's kind of like circular, but basically it's the vertical line test. But instead of vertical lines, you just do a bunch of horizontal lines. So for example, if we look at our pal x squared, right, kind of looks like this. Also, good to talk about it because it's the next section after this one. So notice we failed the horizontal line test, or we failed the horizontal line test because with our horizontal lines, we intersect the graph in two places. The only place we don't would be here where we have the minimum point where it's just, if I could draw, just 0, 0. Okay. So what this says is that basically y's cannot repeat. Okay, so remember with functions, x's cannot be repeat. So if it's a function, remember x's can't repeat. So now if I'm invertible, we tack on y's cannot repeat. So be careful here um, for the, oh, sorry, I'm getting a phone call. I have to answer. Dang it. Sorry, y'all. Just 1 second. Oh, wait, hang on. I pause recording. Okay, I'm back. Sorry, I had to answer a phone call. So hopefully that doesn't mess up the video too much. If not, sorry, just a short intro video. But let me actually zoom out on this. Okay, much better. And auto, even better. Okay, perfect. So what was I saying? Oh yeah, so x's can't repeat to be a function, y's cannot repeat if I'm invertible. So one thing to watch out for the homework is that it will say like, is this graph a function of an invertible something or other? So here, let's say like random example. We've discussed this already in class a little bit, but this by the horizontal line test is invertible, is invertible. However, it fails because it's not a function, right? So it fails the function. So if you just blindly go into like, oh yeah, it passes the horizontal line test, and then you're like, yes, it's invertible, it passes horizontal line test. Then you just have, and it tells you like, no, you're wrong. Just recognize that the reason why the system is telling you incorrect is because it fails at being a function. So just kind of like be aware of that. It's something to be conscious of. So I'm warning you now. So here are two examples. A equals f of 3, excuse me, f is made up of 3.3445 and 5, 6. So if functions are one-to-one, we need to verify that one, x's do not repeat, and then two, the y's do not repeat, right? So one, x's don't repeat, right? That's for function. And then two, y's don't repeat. And that's for one-to-oneness. Oops, if I could write, that would be helpful. Also, just shorthand is literally 1-1. Okay, so my x's do not repeat, 3, 4, 5. And then my y's, 4, 5, 6, also do not repeat. So yes, invertible. Yep, invertible. So y'all pause, do B, and then press play when you're ready. So B, need to make sure, are the x's repeating? -2, 7, 15, we're good there. Now just verify about the y's. Any y's repeating? Ah, we have a 5 and a 5. So it is a function, but not invertible. There we go. Okay. So determine if the functions graph below are one-to-one. Well, here we just have to test, like, do they pass the horizontal line test? What do y'all think? So this one? Yes, one-to-one. This one? No, not one-to-one. Thus not invertible. Remember, what does one-to-one mean to us? It tells us invertible. Excuse me. Sorry, still have that little cough. Invertible. Okay. Gosh, I hate these videos. I miss y'all. I wish I didn't have to do them, but that's okay. It's for you. But y'all just ignore when I make my silly mistakes. Okay, so example 3, show an example that g of x equals x squared plus 5 is not 1-to-1. So show with an example here. Well, we can do this several ways, but if I let x equal -1, then g of -1 is equal to -1 plus 5. -1 squared is 1 plus 5, which is 6. Here, if I let x equal 1, so we all agree that -1 does not equal 1. So this is A does not equal B, right? So if I do g of 1, this is, oops, excuse me. See, I need y'all to catch me with these silly things. 1 squared plus 5, which is 1 plus 5, which is 6. So here, we do have that these two equal, right? 6 does equal 6. But by the definition of 1-to-1, if we have y values that are the same, well, then it better be because we just doubled up on the same x. But that is not the case here, right? We got the same y output, with different input. So that is an example of why we are not 1-to-1. Okay. So keep moving. Inverse function. Oops, pardon me, off screen there. Let f be a 1-to-1 function, then g is an inverse function of f if f composed of g of x equals x, and g composed of f of x equals x. So basically what this means is that what you input is the same output. So basically your f and g are undo the other. Okay, so that's a main takeaway of inverse functions. So like star, highlight, note to yourself, like big mama jamma understanding right here. We love inverse functions because they cancel each other out. Okay. We like inverse functions because they undo each other. A lot of things in math we need to like Command Z, undo. That's where inverse functions come into play. Okay. So the X and Y values switch for domain and range. With that comes the more specific of the domain of F is the range of F inverse, right? Sorry, I skipped over here. We write um, F to the negative first of X. It's actually read as F inverse of X. So that is how I would say that. F inverse of X. So basically, since the inputs and outputs switch, then of course the domain and range F to F inverse switch. So how I like to say it is that if F has the point A comma B, then F inverse has the point, excuse me, B comma A. Like literally, you just bloop, bloop, switch the X and Y. That's it. So we're gonna keep this in mind right here when we show that, actually we're gonna do this one right here. We're gonna use the composition of functions to show that F and G are inverses of each other. So remember, I think of this as like laundry. You put, like you pull clean clothes out of your closet, you wear them, you get them dirty, you wash them, dry them, you put them back in your closet. Okay. F composed of G, G composed of F. That's like your washer dryer. Okay. You are basically undoing the wear of the article of clothing. Hopefully that makes sense. So one way to show that functions are invertible is that you take the composition of both. Okay. So basically, whatever happens in here, it better be like the wash cycle and drying. Whatever is acted upon must also be undone. Okay. So like I said in the last section, what was that? 15? Yeah. When we learned about composition of functions, what do you know? We learned about composition of functions in the next section and now we're using it. Surprise! Uh, Remember, don't assume just because you've done one F composed of G means that you've done the other G composed of F, or fog and goth, as I lovingly refer to them as. Okay, so it does need to be double verified. So I'll do the first one, and then I want y'all to pause the video, try goth on your own, and see if things happen. So I like to start off with going into our function notation and then just string the substitutions. So f of g of x, well, here's g of x, 5 minus x over 3. Now remember that 5 minus x over 3 goes into x for f. So this is negative 3 times 5 minus x over 3 minus x, and then all plus 5. So then note that the 3's cancel, and we now have, let's see, distributing this negative through, distribute, that is x minus 5 and then plus 5. And then what happens with the 5? They also cancel. So yes, what was done was undone. So the times 3 divide by 3, add 5, subtract 5. So perfect. Okay, now again, pause the video, try decompose of f on your own. You should get just x. So you should have stuff cancel in here. Ready, go. Okay, welcome back. So this is g of f of x, or g of negative 3x plus 5 equals 5 minus negative 3x plus 5 all over 3. So distributing that negative, this is, where am I? Yes, sorry. 5 plus 3x minus 5 all over 3. So then what happens with the 5? They cancel, which in turn just leaves us with 3x over 3. And then what happens with the 3's? They cancel because anything over itself is 1. And we are then just left with x again. So yay, they are inverses of each other. So indeed, inverses of each other. Perfect. Okay. And again, we have to do it both ways because remember from the last section, just because you've done fog does not imply that you've done goth. You have to do the double check. Okay, so if for S, the domain is 0 to infinity and the range is negative infinity to 4, if I say find the domain of F inverse, well, remember they just switched. So the domain is the old range, so negative infinity to 4. The range is in bracket 0 to infinity. It is that simple, okay? Literally you just swap them, okay? That's one of those things where it's like on a test or in the homework, you're like, oh, this is hard, 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 hard. And then you get to this question and your brain's like, no, I'm on the route of everything that's hard. So then when you like pull back, you're like, oh gosh, it's that easy? Yes, it is that easy. I love these types of test questions, to be honest, because it's just kind of, I don't know, I don't want to say keeps you on your toes, but it allows me to make sure and verify that you remember the like the definitions, the background things that are actually going on with um the function itself. Right. So domain and range, they just literally they switch positions, right here. Okay. So 2 more pages for this section. So what if I give you a function and I ask you to find the inverse? Well, we'll start by replacing f of x with y. We interchange x and y because remember that's the thing for f to f inverse, the domain and range switch positions, right? That is because for f to f inverse, there's one right here, where'd it go? Remember the x and y switch position. So we are using this idea to help us find and solve inverse functions. Then we basically just solve for the new y, and now you write f inverse instead. So it seems, fairly, I don't know, hopefully it seems easy, but it can get a little squirrely. So first, f of x becomes y. So 3x minus 2. Then literally just say x equals 3y minus 2, right? Swap out or switch your x and y. Now solve for y. So that's something the 2 divide by 3, x plus 2 over 3. And then up and over, just switching back out to say f inverse of x is now x plus 2 over 3. You did it. Yeah, hopefully you thought that was easy. Okay, pause and try B. When you're done, press play on the video. Okay, let me see colors for effect. So y equals the square root of x plus 6. Now I'm going to switch my input-output letters. And we're going to solve for y. Remember, y is in jail, y is in prison. So we want to undo the square root. So how we do that is by squaring both sides. So now x squared equals y plus 6. And then last but not least, we subtract the 6. So x squared minus 6 equals y, and then loop up and over. F inverse of x is equal to x squared minus 6. Now, I know what you're thinking. Leslie, you said on the first page that our friend y squared is not invertible. And that's right, I did say that. That is true. So that is why sometimes in math there's a little bit of like jazz hands, hand waving that happens. Because y'all know we have to undo squares and square roots all the stinking time. So when we need this to happen, we force a domain to be from 0 to infinity. Okay, we force a domain to be from 0 to infinity. So that now when I cover up just the left-hand side and I'm only looking at the right, so I only have like a single branch, if you would. Now we do pass the horizontal line test. So that is one of those like math caveats that you might find annoying. You're like, ugh, right? One more thing to learn. But it's a way that we like circumvent the challenges of the math that basically like force what we need to happen. Okay. If you'll notice, there's a lot of that happening in math. We just kind of like use versions of one to make what we need happen. We change the domain, restrict the domain to get what we need to happen, right? We do other things, right? A lot of math is just like forcing what you need to happen, but in like math legal ways. Does that make sense? Like lots of math loopholes. Okay, so C, again, pause the video, try C. When you're ready, press play. Okay, so y equals x plus 3 over x plus 7. Now we're going to switch. So x equals y plus 3 over y plus 7. Okay, so remember, working backwards, what are we solving for? Y. How many y's do we have? 2. Womp womp. Bad news bears. Right? That makes us sad. And on top of that, we have a fraction. Who likes fractions? Nobody, and liars. So, I don't know, we don't really like the fraction thing happening. It's not helping us get us down to a single y. But one thing we can do to at least get rid of the whole fraction situation is multiply that sucker over to the left. So x times y plus 7 equals y plus 3. All right, now the next thing we have going on is that this y is now in jail. But do we know how to get it out of jail? Yes. If we distribute the x, then those parentheses can drop. Perfect. Okay. So one thing, we're gonna go on our way, working in our favor, but we still have 2 stinking y's. Dang it. But what can we do that is at least like moves us in the right direction? Well, moving us in the right direction would at least be getting the y's on the same side. Let's get all the y's on the same side and kick everything else to the other. Really doesn't matter if you move the y's to the right side or the left side. I just moved them to the left, or I don't know. I felt like it, I guess. Okay, but still, okay, great. They're on one side. Woohoo, what do you do? What do we do with that? Like, who cares? Remember, if I can make a single x 2 things, right? X and x. This is an x on the outside. Now we have 2 x's. So if I can make one thing 2, we can make 2 things 1 by factoring. Remember that this is distributing. The opposite of distribution is factoring. So we just factor out a y. So the reason why we want y's on one side, everything else on the other, is because now here on the left side, there's a y in every term, and that's a common factor. Okay, and therefore that is why we can pull one out of each term. Okay. And then up and over. Sorry, I'm running out of space. Okay. One last step, technically. Divide by the x minus 1. So 3 minus 7x over x minus 1. Last but not least, just switch y for f inverse. 3 minus 7x over x minus 1. For some reason, just historically, what I've noticed, that this part right here will give students grief. Okay, so if that's you, that's totally fine. You're completely normal, right? You're just like everyone else. Whether that makes you happy or sad, I'm sorry, it just is. But remember that if you can distribute, you can also factor, right? So just remember that factoring is available to you. Okay, last page for this section. So inverse functions. Remember here that if f has the point AB, f inverse has the point BA. So that is why the inverse functions reflect over the identity line because you have this flip, this reflection, this whoop, flop. So that is why if blue has 0, 1, red has 1, 0. If blue has 1, 6, then red has 6, 1. Right? And then so on and so forth. Like if we said that was for sake of argument, it's not, but I'm trying to find one. Okay, maybe this one right here. -3, -1, and then -1, -3, right? You literally just switch them over. It's really that easy. Okay. So, or hopefully, I don't want to like make that sound like duh. I mean, it might, I know you're learning, so sorry. I don't mean it in any kind of like negative implication. Hopefully, I should say, I hope you find it that easy. So, example 7. Excuse me. Find the inverse of f of x equaling x cubed minus 2. Then we're going to graph f and f inverse on the same graph. Okie dokie. So remember our steps. 1, change f of x for y. Y equals x cubed. Oops, not -2. Then we switch the letters around. Now we solve for y. So add the 2 over. Cube root both sides. Cube root both sides, right? So the cube root and the cube undo each other. I like the sound effects. All right. This is the cube root of x plus 2 equaling y, which is f inverse. Perfect. Okay, great. So what I would rather do is just find some points on f, and then we're just going to do the old switcheroo for the points on f inverse, and then connect the dots essentially. So let's pick some good numbers. So if I have f of x equaling x cubed minus 2, so here's my x, my y. I don't know, let's do -1, 0, 1, 2. How does that suit? Hopefully it suits you well. Again, see, this is why I don't like the videos. I like in person. I like your feedback. I miss you. Okay. So -1 cubed minus 2. -1 cubed is -1. Minus 2 is -3. So this is 0 cubed minus 2, or -2. I'm also scared I'm gonna just do my silly human errors and just mess it up, and y'all be screaming at the video. Like, you silly. But anyways, we digress. Let's see. 1 cubed is 1. Minus 2 is -1. 2 cubed minus 2. 2 cubed is 8. Minus 2 is 6. So f has the point, not the only point, but -1, -3, 0, -2, 1, comma, -1, and 2, comma, 6. Okay. Again, these are just the points we're doing. That's not the only point. Okay, -1, -3, 2, 2, 2, 2. 0, -2, 2, 2, 2. 1, -1, and 2, 6. 2, 6 up here. Okay. Because remember the parent function, y equaling x cubed, I should do it in a different color for visual effect. So sorry. Oh, and I should do it to where you can see it. Silly. Silly. Remember that x cubed, the parent function, looks like this. So by our transformations of graphs, remember this is just the parent function shifted down. So essentially we've got this action happening here. But pretend like I can draw. Y'all know I can't draw. Oh yeah, there we go. Nice. Okay. So if f has these points, then we know f inverse will have, excuse me, f inverse will have, y'all pause the video real fast, write down your own points, and then play when you're ready. F inverse will have -3, -1, -2, 0, -1, 1, and 6, comma 2. Ta-da! So we just plot. Okay, so -3, -1, -2, 0, -1, 1, and 6, 2. Okay, there we go. Oh, yeah, okay. But y'all graph better than me. Y'all graph better than me. So if it's 6, 2, then we also have -6, 2. -6, -2. There we go. Remember that y cube root x looks like this. Oop, maybe a little. There we go. Looks like that. So it's just this shifted right to the left. Oh, again. Oh, Lord. Sorry. So you can't see that. I'll leave. So this is the parent function. All right. So this is the parent function shifted to the left. Ooh, cool, right? And again, notice we are, let me get a different color. If I could draw, oh man, I'm pretty good at drawing today. Who knew? Ta-da. There we go. Nice. Perfect. We are right across that identity line. Yay. Oh, also going back, so if you were to, let me grab my page. So sorry, bear with me. If you were to ask, like, verify these two things are inverses, I mean, you can do this. That's great. Yeah. Go up. But you can also, like, if you have, here's this, you can also find its inverse and just compare it to G. Does that make sense? Hopefully. Like here here's F, we found its inverse. So if I was given a G, I would just say, okay, like, is the other given this function? If it is, then yeah, they're inverses. If it's not, then they're not. And hopefully that makes sense. I think there's a homework question on it, but I digress. Also, to go back to whenever we take a square root of something, because of this like hand waving math loophole, this is the reason why whenever we square root something, we have to add the plus or minus. Because to go from saying that x squared is undone by root x and root x undoes x squared, because we have to restrict the domain. We only have the right hand branch. So this is why whenever we take the square root of something, I'm just making up a random example, right? If I'm totally making this up and I'll do a bad job at it. 3 equals x squared minus 1. If we're solving, right, we add 1. So 4 equals x squared. We take the square root of both sides. And then I always prompt, but what do we not forget? Oh yeah, plus or minus. So that is plus or minus 2 is equal to x. Because we restricted x squared to only have half to force this inverse situation so that a square root does undo a square. But because that's not the true nature of an x squared, it has both sides of the branches, right? It is a bowl, not like a exponential looking thing. This is why we always have to do the plus minus. Just if you're curious, kind of like an afterthought, if you're a why knowing type person, you like to know the why behind things. There you go. There's 16. Ooh, go on.